Example 4D. Our system is 2x plus 3y plus 5z is equal to 21. X minus y minus 5z is equal to -2. And 2x plus y minus z is equal to 11. Okay, let's write down the first augmented matrix. Okay, so the first equation will correspond to the first row of the matrix. There is a 2 in front of x, 3 in front of y, 5 in front of z, 21 on the other side. Okay, there is a 1 in front of x, -1 in front of y, -5 in front of z, -2 on the other side for the second equation. And then the last equation, there's a 2 in front of x, 1 in front of y, -1 in front of z, 11 on the other side. Okay? All right, so let's start our Gauss-Jordan elimination. Okay, we are going to start in the first column. Okay, we're going to look at the main diagonal element. Okay, so there's our main diagonal elements, 2, -1, and -1. So for our column, the main diagonal element is 2. We want that to be a 1. Okay, the easiest way to make that happen is to switch row 1 and row 2. Okay, so if we flippy-flop here, the 1 will go right there. Okay, so in my second matrix, okay, I'm going to switch rows here. Okay, I'm going to write my row operation to go from the first matrix to the second matrix. We are going to switch rows 1 and 2. Okay, so there's my shorthand for that. Okay, and then that will give us what? Well, the third row isn't going to change. It's not involved at all. And then switch 1 and 2. So your current first row will become your second row. And then your current second row will become your first row. Okay, so that's what it's going to look like for your second matrix. Okay, all right, so we've achieved the 1 on the main diagonal, and now we can start on zeroing out the rest of this column. Okay, all right, so I'm going to take this first 2 right here, and I'm going to turn that into a 0. Okay, so I'm going to use the third row operation to get my 0. Okay, so to do this, we are going to make a change to row 2. Okay, so to do that, the third row operation says you need to add to row 2 a multiple of another row. Okay, so again, which row are we going to use? Well, it always corresponds to the same column you're in. We're in column 1. Here's the 1 on the principal diagonal. That 1 resides in row 1. So that's the row we're going to multiply by. Okay, since we're trying to get rid of a +2, we're going to multiply by -2. Okay, so our row operation is going to be -2 row times row 1 plus row 2 becomes the new row 2. Okay, because if you take row 1 and multiply by -2, that would put a -2 right here. You add it back to the second row, you add it back to +2, you're going to get your 0. Okay, all right, so our third matrix will be, okay, in this step, row 2 is changing, so we're going to leave row 1 alone. We're going to leave row 3 alone. And then I'll go out to the side and do the work for the new second row. All right, we're going to do -2 times row 1. So we're going to multiply all of row 1 by -2. That's going to give us -2, +2, +10, +4. Okay, add this to the second row, which is right here. Okay, so add it to 2, 3, 5, 21. We're adding. Okay, and we will get -2 plus 2 is 0. 2 plus 3 is 5. 10 plus 5 is 15. 4 plus 21 is 25. Okay, there's your new second row. All right. Okay, keep going. Okay, still working in column number 1. Okay, now we've got to zero out this guy. Okay, another application of the third row operation. Okay, so for our fourth matrix, okay, we're going to make a change to row 3. Okay, so we need to add to row 3 multiple of another row. Okay, again, we're working in column 1. So that means we're going to multiply row 1 by something. They correspond. Okay. We are trying to get rid of a positive 2. So we're going to multiply by negative 2. So very similar to the last step. Okay. So our row operation for this step is going to be negative 2 times row 1 plus row 3 becomes the new row 3. If I multiply row 1 by negative 2, that will put a negative 2 in this position. You add it back to row 2, which is to row 3, which is positive 2, you're going to get the 0. Okay? All right, so in my next step, my new matrix, I'm only changing row 3, so I'm going to leave rows 1 and 2 alone, so I'm just going to rewrite them. Okay, and then now I'll go do the work for this one. I'm going to do negative 2 times row 1. That is going to be, let me just write all this down. Like I said, it's in your best interest to write everything down. There's so much arithmetic, you're less likely to make a mistake if you write it down. So negative 2, positive 10, positive 4. We are going to add to it the third row. The third row is up here, 2, 1, negative 1, 11. Okay, so if we add, we're going to get 0, 3, 9, 15 if we add everything. Okay, watch your signs. Okay, so here's your new third row. And the first column is complete. Okay, 1 on the main diagonal, 0s elsewhere. Okay, time to move to column 2. Okay, so move on to column 2. First thing to take care of is the principal diagonal element. Okay, we need that 5 to be a 1. Okay, easiest thing is to multiply or divide row 2 by 5. Okay, so divide row 2 by 5. And good for us, the entire row is divisible by 5, which means we won't end up with any fractions. Okay, so I'm going to come up here, okay, to get my fifth matrix. Okay, I am going to take row 2, divide it by 5, and that's going to become the new row 2. Okay, if you go back to your previous matrix, we are only changing row 2. So rows 1 and 3 will stay put. Okay, so you can go back to your last matrix where you left off. Go ahead and copy row 1 down and copy row 3 down. Okay, so let's do that. All right. Okay, so now I'm going to go out to the side. You don't have to. You could actually do this part in your head. But currently row 2 is 0, 5, 15, and 25. And then I'm going to divide that entire row by 5. Okay, so the result will be 0, 1, 3, 5. Okay. All right, so moving right along. Okay. So still in the second column. Okay. Now we've got our 1 on our main diagonal, so now we need to start zeroing out the rest of the column. So we're going to change that negative 1 to a 0. Okay. Again, you can do the third row operation here. Okay. So that's what you should do when you're getting your zeros. Okay. So we are making a change to row 1. So that means you're going to add to row 1. Okay, a multiple of another row. Okay. Again, you're in the second column now. Okay, so that means you should be multiplying row 2 by something. Okay, those things always correspond. Okay. You want to cancel a negative 1. So the opposite of that is positive 1. Okay, so it's a little weird here, but you're multiplying by positive 1. Okay. And if you look at this, this is really row 2 plus row 1. Okay, you're adding 2 rows. Okay, if I add the first and the second rows here, okay, I'm going to get my 0. Okay, but keep in mind that's going to replace row 1, not row 2. Okay, and I did tell you, keep that in your little pocket of tricks with these matrices. Okay, at any time you can add or subtract any 2 rows to replace one of the ones involved. Okay, like if I let me make this clear. If you were adding rows 1 and 2, it has to replace either row 1 or row 2, okay? Can't involve row 3 at all, okay? All right, so let's go ahead and do that. Row 1 is changing, so I'm going to leave row 2 alone. I'm going to leave row 3 alone. And then I'm just going to add the 2 rows, okay? If you don't need to work it out, that's fine, okay? I'll just write it down for you. Here are the 2 rows. And then I'm going to add them together. Just watch your signs, okay? So we're going to get 1, 0, -2, +3. And that will be your new first row. Okay, there we go. All right, continuing on, second column. Now I've got to zero out that 3. Okay, so third row operation again. Okay, moving on to the next matrix, we are going to be changing row 3. Okay, so that means we are going to be adding to row 3 a multiple of another row. Okay, we are in the second column, so that means we need to be multiplying row 2 by something. Okay, and again, what do we multiply by? Well, since we're trying to cancel a +3, we need to multiply by a -3. Okay, so there's our row operation. Okay, -3 row 2 plus row 3 becomes row 3. Okay, and we know it's going to work because if I multiply row 2 by -3, that will put a -3 in this position. Add it back to +3, you'll get your 0. Okay, so we're changing row 3, so I'm going to rewrite my 7th matrix. I'm going to leave rows 1 and 2 alone. And then I'm going to do the workout to the side for the new row 3. Okay, we're going to do -3 times row 2. Okay, so that will give us 0, -3, -9, -15. We're going to add this back to the third row, which is 0, 3, 9, 15. And look what happens. Okay, everything cancels out. And we're going to end up with a row of zeros. Okay, so again, this is something that you saw when we did the smaller systems where we had 2 equations and 2 variables. Okay, we did see cases where there was a row consisting entirely of zeros. Okay, now just think from the 7th matrix, you completed columns 1, you completed columns 1 and 2. You should move on to the third column, and you should be interested in turning this 0 into a 1. But we know from prior practice, at least with the smaller systems, that's not going to happen, okay? Anything you try, so for example, like switching rows or something, it's going to undo your previous work. So there's no way to get a 1 in that position, okay? So you stop, okay? And you know, you can interpret the solution like we've done before, okay? When we did the smaller systems and there was a row entirely of zeros, including on the right side of the vertical bar, that indicates infinitely many solutions, okay? Why? Okay, because again, you're looking at this first column, numbers in front of X, second column, numbers in front of Z, third column, first column, numbers in front of X, second column, numbers in front of Y, third column, numbers in front of Z, okay? So when you translate that last line, it's 0 times X plus 0 times Y plus 0 times Z is equal to 0. That tells you 0 equals 0. That's a true statement, okay? So that voids no solution, because if it were no solution, you would have gotten something like you did in example C, where you got 0 equals 4. That doesn't make any sense. But if you get something that makes sense, that indicates infinitely many solutions. Okay, and again, if there were exactly one solution in actual X, Y, and Z, you would have ended up with the identity matrix on the left of the vertical bar. Okay, any row consisting entirely of zeros is going to be infinitely many solutions. Okay, again, make sure you recognize the difference between this and no solution. Okay, so I'm flipping back to part C. Okay, In part C, we got 0, 0, 0, but then, so if you translated this last line, it would be 0 equals 4. Nonsensical. Okay, so that's the case of no solution. Okay. All right. You have to parameterize because this is infinitely many solutions. Okay. We are now in a bigger system. Okay. It is a little more difficult to parameterize. Okay. I am going to parameterize on a separate page. Okay. You start by translating these top two lines into equations. Okay. So to parameterize, okay, I'm translating these two lines back into equations. Okay. So the first one's telling me 1 times x plus 0 times y plus -2 times z is equal to 3. Okay, so if I simplify that, that's going to be x minus 2z is equal to 3. Okay, do it to the second row of the matrix as well. Okay, we would get 0 times x plus 1 times y plus 3 times z is equal to 5. Simplify that, you're going to get y plus 3z equals 5. Okay. All right. So once you've gone back into equation mode, okay, now we can work on the parameterization. Okay. We are going to focus on these equations. Okay. Now, we are going to translate this into something involving t. T is your parameter. And when you did a smaller system, the 2 equations and 2 variables, there was kind of 2 different ways you could do it depending on whether you solve for the x or the y. But now that you've gotten into a bigger system with 3 equations and 3 variables, only one of the variables can become t. Okay, this is how you choose it. Okay, these are the equations we translated from the matrix. Okay, both of them have a z. Okay, so z is going to become the t because both equations involve the t. Or sorry, both equations involve the z. Okay, that's why z is t. Okay, I'll even write that down. Z is equal to t because both equations involve z. Okay, so z is going to be the t. Okay, now to parameterize it. Okay, now what we're going to do is we're going to go to each equation and we're going to solve for the other variable. Okay, so like in the first equation here, okay, we're going to solve for the x, not the z. Okay, in the second equation, we're going to solve for the y, not the z. Okay, so if I do that, okay, I'm going to come down here. Okay, my first equation, x minus 2z is equal to 3. Okay, I'm going to solve for x, so move the 2z over. Okay, I'm going to get x equals 2z plus 3. Okay, and then for my second equation, okay, go back up here. I'm going to take this equation and I'm going to solve it for y. Okay, so we have y plus 3z is equal to 5. To get y by itself, I'm going to move the 3z over. So I'm going to get y equals -3z plus 5. Okay. All right. So now that you've done that, you can write down the parameterization. Parameterization has to involve only t's. No x's, no y's, no z's. Okay. So we're going to write this as an ordered triple. Okay. So usually we put the x coordinate, then the y coordinate, then the z coordinate. Okay. All right. We know that z is the t. Okay, so then, and I'm probably going to need more room here. So then, if we know that, go back to the x coordinate. To get x, if you know that z is t, then the x coordinate is going to be 2t plus 3. Okay, so it's going to look like that. That's the x coordinate. Okay, and then lastly, go to the y coordinate. Okay, if you know that z is t, then y is going to be -3t plus 5. Okay, And that's your parameterization right here. Okay, so remember, this is corresponding to your x coordinate. This is your y coordinate. This is your z coordinate. Okay. You can, if I ask you for a specific solution, meaning what is one specific x, y, z triple that would make the system true, meaning if you plugged in those variable assignments into all three equations, you would get 3 true statements. Okay. I'll go back up here because I'm running out of room. Okay. So if we want a specific solution, remember all you have to do is pick a t-value. Okay. Randomly. Okay. I don't know, I'll pick 0. 0 is always easy to pick, okay? So if t is 0, okay, then your x value is going to be 2t plus 3. So you would get 2 times 0 plus 3. You would get 3 for x, okay? And then your y, okay, remember y is negative 3 t plus 5. Okay, so if we chose t to be 0, then that means y would be negative 3 times 0 plus 5. So y would be 5. Okay, so one specific solution to the system would be x is 3, y is 5, and z is 0. Okay, so that's just, it's definitely a little more challenging to parameterize if you have a bigger system, okay? But again, the way you choose which variable is the t, okay? Once you've translated your matrix back into equation form, okay? The equations should both involve one of the variables, okay? That is going to be your t, okay? So since both of these involve z, that was my t, okay? And then you take each equation and you solve it for the other variable. Okay, so here we solve for x, we solve for y, okay? And then we just wrote it down as an ordered triple. Okay, we know that z is the t value, and then knowing that z is t, we translated the x coordinate in the y coordinate. Okay, and again, to get one specific solution, make up a number for t. Okay, plug it in, plug it in, plug it in. It'll give you a specific x, y, and z that will be a solution to the system.